Hi all, welcome to our industry webinar on the mining and minerals processing industries. We'll just wait for participants to roll in. I see they're streaming in now, and I'll just wait for that to stabilize and then we'll get going. Okay, let's get started. Big welcome to all of you who have just come in to our webinar on 3D printing in the mining industry. Today, we are going to find out how additive manufacturing can transform a complex system of parts into digital files that can be stored in the cloud and printed on demand and on site. My name is Anthony Rosengren, and I'm an Markforged Applications Engineer for APAC. We also have with us Amgad Yaqub from Central Innovation, who will talk about how design software is changing the industry. So I'm just pausing my printer in the background there. Okay, so for the agenda, what we're going to talk about today is firstly the industry overview. We're going to talk about market pressures and market projection. We're then going to talk about how additive manufacturing is used today in the industry. We'll then move on to talk about the future state of additive manufacturing in mining and have a deep dive into the role of Markforged using case studies. We'll have a look at an applications guide, and then I'll hand over to Amgad, who will talk about engineering 4.0 from the software perspective, and Amgad is from Central Innovation. And finally, we'll have a brief introduction to Markforged. So let's have a look at the mining industry overview. So what happens in mining? So a lot of you will be from the industry, some of you won't, but on a very quick and basic level, we have open cut and we have underground. Within open cut and underground, we have various units, including drill and blast, minerals processing, excavation, and transport. So the mining industry is diverse. It's easy to lose sight of what goes on and what goes into the whole ecosystem. The business units who are part of the industry include civil and mining engineering consultants and contractors, environmental consultants, and of course, OEMs who supply the equipment needed for all of these operations. Let's move on to have a look at some of the market pressures on this industry. Internationally, the worldwide industrial services sector is expected to reach 44.1 billion by 2025. Locally, Australia's mining industry has delivered a 10.4% share of the Australian economy in 2019 to 2020, making it the largest economic contributor with a 202 billion GDP, according to the Australian Bureau of Statistics. The ABS saw 4.9% growth in the industry in 2019 to 2020, which was attributed to iron ore's strong year of demand due to international supply issues and increased demand from China. Higher capacity oil and gas extraction facilities also boosted the mining industry in this period. While this general trend has been growth, there are some more nuanced trends that it is important to understand. The first of this is leaner and greener manufacturing. As we tighten our emissions targets, there is pressure on reducing waste and finding new ways to manufacture components more efficiently. The second is desire for on-demand and on-site solutions. So when there are disruptions in maintenance, repair, and operations, we can no longer afford to shut things down while we wait for a new part to arrive. We then have a skilled laborers shortage. So it has been the case for a long time now that graduate mining engineers are in short supply. This is largely because a lot of people would rather work in the city than on a mine site or do FIFO. In addition to this, even if an OEM is based in a city, it is increasingly difficult to find machining talent to support that manufacturing. The next is customizable and replicatable solutions. So as mining equipment is becoming more sophisticated and niche to each site, we need to be able to come up with solutions on site that are both custom and able to be repeated. The next is that demand for coal is stagnating. Coal has traditionally been a massive part of Australian mining, and as demand for coal decreases, the demand for metals like copper increase, and companies are having to quickly change their operations to accommodate this change. And finally, focus on productivity. According to IBIS World's Mining Industry and Trends report, the mining division is anticipated to increasingly focus on output and productivity over the next 5 years. The industry's investment pipeline is slowing as existing major projects reach completion and firms bring new capacity online. Therefore, productivity of existing mines is essential to keep up with minerals demand. And finally, supply chain issues, which are hitting a lot of industries. For the mining industry, with its remoteness, securing the supply chain has always been difficult, and these days it's even harder. Conventional supply chains have multiple stages to get parts from point of origin to point of need. Each step adds cost, lead time, and existential risk of that part getting delivered. This situation makes it nearly impossible to respond to the challenges we've outlined relating to manufacturing agility and changing market requirements. We'll learn later how 3D printing with cloud solutions can help to overcome this. So we can talk about issues that need to be addressed until the cows come home. But what is happening to solve these problems right now? Let's have a look at the current adoption of manufacturing in the mining industry around the world. Caterpillar is a good place to start, in that it is a leading manufacturer of heavy equipment by revenue, pulling in $54.7 billion in 2018. The Fortune 100 company began using 3D printing in 1991 and gradually expanded the use of technology for prototyping purposes over time. This was done through team meetings and internal employee contests to design end-use parts for 3D printing. Moving on to Sweden. So Epiroc, a Swedish infrastructure and mining equipment manufacturer, has introduced a project focused on 3D printing spare parts for the mining industry. Anders Johansson, product manager at Epiroc, said that 3D printing allows companies to transfer digital models around the world in minutes to manufacture spare parts right on the spot where they are needed. For Epiroc, the key benefit has been in digital inventory storage, enabling manufacturing of spare parts on demand. This, along with other things, saves warehouse storage and transportation costs, which are some of the reasons why more and more industries are integrating 3D printing into their manufacturing chain. And what you see here is one of the parts that was printed on demand and on site. So moving quickly, but still in Sweden, Sandvik is boosting research spending on 3D printing as the world's largest maker of metal cutting tools expands capabilities in a market that is set to grow ninefold to 21 billion in a decade. And closer to home, ThyssenKrupp's new tech center in Singapore, together with the existing tech center in Germany, is focusing on innovations around additive manufacturing in metal and plastic technologies for customers in mining and other heavy industries. ThyssenKrupp will provide a complete range of additive manufacturing services, from part identification diagnostics to project delivery and training and capability building. In Finland, Metso is a provider of equipment and services for sustainable processing and flow of natural resources in the mining, aggregates, recycling, and processes industries. Most of the company's goals is to become a leader in digital technologies, and it has taken another step towards that goal with the release of the first valves made with 3D printed parts. The 3D printed metal components in the valves allow them to perform in an especially demanding application that requires them to withstand numerous, fast, open-close cycles without maintenance. And Volvo. Volvo are printing end-use parts and spare parts for their machinery. They also are using additive manufacturing for projects like concept machines for their emissions-free quarry projects. So we've had a look at what's happening in the mining industry with additive manufacturing right now, but what about the future state? So before we move on to the future state, let's have a look at the current state. So if we have a look at how to produce a product, you go from design to prototyping to tooling to production and finally to the end product. But within that process, you've got so many steps including fixture fabrication, creating jigs, logistics, you've got prototype tooling, you've got CAD, CAM, supply chain and mold making. And then once that product is finally produced, the solution isn't simple from there. Even when you have the final product, you need to manufacture that product. You need to start with the raw material, you need to manufacture it, you need to ship it, and you need to store it in inventory. You don't need to do this anymore. With digital inventory, you can have these parts on demand. If you want a prototype, if you want the end product, if you want the tooling, you simply go from design to print and you have the final part. And we'll give you plenty of examples of how this is happening at the moment. So the first example of this being done now is an example of an industry that is analogous to mining, and that is the military. So a team of US Marines 3D printed a part for the F-35 stealth fighter, saving 70 grand in costs for a whole new landing gear door. And using Markforged 3D printers, they produced the landing gear part in a matter of a couple of hours and were able to successfully install it on the grounded F-35 and get the plane back into the air. Like the military, mining can be a lonely game with a lot of remote sites. As you know, mines generally aren't near major population centres. Often the expertise for projects in WA, Papua New Guinea, or even Mongolia will come from Melbourne, Brisbane, or Perth. Decades ago, it was common for families to live near mine sites. Things changed, and now FIFO is the norm. But in many cases, there have been serious consequences to the mental health of workers and their families. What if you could have your engineers remain with their families with the ability to send parts over the cloud, have them validated on site and iterated as needed? What if companies could reduce their dependence on FIFO workers through a cloud solution? What a lot of companies are moving towards in other industries in Australia is the use of the cloud as a way to send parts digitally and print on site. With Markforged cloud solution architecture, engineers upload or update STLs from an office that could be thousands of kilometers away, while service technicians hold the digital inventory to their local printer as needed. So what about the current adoption of Markforged in Australia and internationally? The first, case study that we're going to have a look at, or company that is adopting the technology, is Russell Mineral Equipment. RME are a global leader in the design, manufacture, and supply and operation of mill relining technologies and services. I had the pleasure of visiting these guys in Toowoomba and saw how they have been able to adopt Markforged technology. One of their products is their Thunderbolt recoilless hammer. This product allows for faster movement between bolts and faster alignment, along with increased hammer preloading compared to conventional methods. Reducing downtime is what matters to minerals processing personnel. So RME have designed the Thunderbolt Magnum recoilless hammer to deliver faster linear bolt removal, even more reliable performance, and efficient enhanced serviceability. Raptor Tech is another company. They design and manufacture customized and ruggedized industrial Internet of Things sensors for mining machines and other harsh environments. So they custom print each sensor enclosure to suit the customer requirements. Printing on the Markforged Onyx filament provides the required structural and thermal properties with none of the upfront tooling costs. The next project was a collaboration between Mech3D, Westrack, and Telstra. The mission was to roll out 4G LTE network at Roy Hill, the innovation team at Westrac wanted to pursue additive manufacturing at the same time as validating the capabilities of 3D printed parts for future projects. So the issue here was there was a team of vehicles that were all autonomous, laying out this network. However, if one of these vehicles failed or a component on one of these vehicles failed, all of these trucks had to stop because they were autonomous. So the solution was to 3D print a protective bracket to isolate movement of the cables between the connector and the support cable itself, because this is where the failure was happening. The Markforged printers were able to provide reliable, structurally sound parts. So on the left here, you can see the parts being printed in a batch, and on the right, you can see the end-use part. Moving on, Imdex Limited is a global mining tech company. The company develops drilling optimization products and cloud-connected sensors to provide real-time rock knowledge and quality data. Imdex clients include drilling contractors and resource companies within the global minerals industry. So there are a few little, I guess, case studies here to have a look at. The first on the top left there is a PCB programming jig. So this jig was designed to assist with the programming of PCBs in a production environment, allowing PCBs to be easily clipped in and held, while also housing the programming electronics. The second, moving on to the top right, is the lid cover. 3D printing was used to quickly iterate the design to create a seal against the crusher jaws. The somewhat intricate geometry of the seal type feature made 3D printing a much more cost-effective solution than the original machining process, while still maintaining very good strength. The next down the bottom left is an outlet chute. A machined outlet chute design was revised to add a safety grille feature. This grille was designed in a way so that it maintained free material flow through the chute, and due to its complexity, 3D printing was used to prototype and for the end-use part. And the final little case study there is an interlock housing. So high-strength 3D printing was used to quickly iterate housing designs for the safety interlock switch for a rock crusher. The housing protects the interlock from loose rock and gravel and tampering, and is due to the small and complex design. This was an ideal candidate for 3D printing the end-use part. So for this case, where the customer can't be named, this particular application is for downhole surveying equipment, which needed power, and battery was the only solution to provide that power. The suppliers for this were not able to deliver the previous solution, so this is a legacy part. They tried to print in ABS, but couldn't produce usable parts. And there was no standard solution for a better replacement. With this custom solution with high strength additive manufacturing, rather than changing the batteries one at a time, they were able to put the batteries in series to save time and improve safety. And here you can see these parts in production. I believe they made 200 for the project, and you can see the end part there on the right. One of the biggest benefits of 3D printing for mining OEMs is the ability to make custom tooling. Goering was able to add more cutting blades to this tool and therefore increase cutting speeds because of the ability to run water through this metal 3D printed part. And moving to the construction industry, which is very similar to the mining industry in a lot of ways. But basically, Maconex manufactures professional grade tools, generators, and construction equipment. Constant innovation is a large part of their strategy, and which means rapid, constant prototyping and the need to produce custom end-use parts. These are all made with Markforged's composite solution. One of my favorite case studies is Siemens. So Siemens, being in the energy industry, needed a cutback tool for working on some of their turbines in the field. After designing a prototype, Siemens requested initial feedback from field engineers and redesigned the tool with suggestions in mind. Pictured above is the updated version, which is easier to handle and more ergonomic. Just one of these tools saved the company approximately 8,000 US dollars, and there are several of these tools in the field currently as end-use parts. Volumetric is a New Zealand company that basically produce parts for motor racing equipment. I've included this case study because these parts were specifically designed to be able to withstand the chemicals involved in these engines, as well as the heat, with the continuous fiber being routed through them. A lot of my mining engineering friends have mentioned that on site, pumps are an issue, pump breakdowns. So I've included this case study as a, these guys are an OEM of pumping and vacuum solutions. So these guys are able to print certain components that would be too expensive to machine. And we have the US military. So the US military and militaries around the world are using mark-forged high-strength additive manufacturing to secure their supply chains. Like in mining, in military operations, the ability to keep going without interruptions due to maintenance and operations is critical. And these guys are working on a few different applications. One of them is directional explosives, which has some analogous applications to the mining industry. So the challenge for the military, like mining, is to recover faster when parts break, to operate with less on-hand inventory, to save money from transporting fewer parts and machines around the world, and to have rapid response times when supply chains are disrupted or have long lead times. So Markforged actually have developed a solution specifically for the military, although this solution can easily be transferred to the mining industry. We can't reveal it yet, but this will be revealed in Land Forces in Brisbane, which goes from the 1st to the 3rd of June. So very excited for that event to happen, and I'll be there, so looking forward to it. Let's have a quick look at an applications guide. We don't have a lot of time to go through the detailed applications guide, but basically we have myself and our partners with applications engineers all around Australia who can help to identify, I guess, the pain point and what would be a good application for you for high-strength additive manufacturing. This is one of my favorite little tricks with 3D printing with Markforged, and this is hybrid parts. So hybrid parts are great for overcoming size limitations. And a great example is in custom tooling. So if you're creating custom tooling, you need hardness in certain spots, but you also need the tools to be light. So what they've done here is they've put that hardness in the spot that it needs to be, whereas the rest of it is printed in a composite. So there are numerous examples of this sort of method, but being used by companies around the world. But it is really nice when you see that custom tooling working. Okay, end-use parts. So we have a few case studies for end-use parts, especially when legacy parts are an issue. So for this particular company, Stanley Black & Decker, there was a legacy part that was not being produced anymore, and they were able to 3D print that part for the limited volumes that they needed. We move on to construction machinery. So 3D printing can be used for spare parts and fit outs. So some applications could include communications, routers, servers, monitors, and instruments. Explosives. So Onyx ESD, so that's one of our materials, electrostatic discharge, can be a great material for the manufacture of explosives because of its material properties. And if you're interested, you can reach out to one of the applications engineers to discuss the applications for this particular area. Environmental monitoring. So we see often environmental equipment needs to be customized. And we see that whether it be universities, construction sites, or mining sites, enclosures for environmental monitoring systems is a very popular application for Markforged high-strength 3D printing. And safety, which is arguably one of the biggest areas in mining. So coming up with end-use parts for safety, to be able to make these parts quickly and iterate fast, all helps to improve the safety on mine sites and construction sites. And testing equipment. So that's one of the biggest, I guess, most common applications of Markforged is in testing equipment. So whether it be CMM fixtures, wind tunnel testing, work holding, and alignment jigs. Okay, I'll now pass off to Amgad. So he will take us through some of the software aspects of engineering 4.0 in the mining industry.
Thank you, Anthony. Let me just share my screen here. Right. Thank you, Anthony, and thank you, Markforged, for having us presenting in this webinar. My name is Amgad Yacob. I'm a senior field engineer with Center Innovation, and I will just take you here one step back before 3D printing, looking into the technologies that work behind the scene till you get to the 3D printing step. So let me just go here to my agenda. And in my agenda, I will present mining industry challenges, engineering 4.0, 3D experience platform, center innovation overview, case study of design to 3D printing, success stories, and we will end this session with the Q&A session. Right, so we were speaking and listening to our customers and ask them about the challenges that they have in the mining industry. And the first challenge, as you may all know, downtime cost is very high. They don't afford downtime or breakdown without if it is not in planned maintenance. So the resolution here, they need an easy-to-use, reliable, powerful design to production tools. Second challenge, accessing data anywhere, anytime, and on any device, but not for everyone. So we need, as you heard from Anthony, we need something on the cloud. Relying on your own PC or your own laptop to get or store all the data, or even relying on a server that sits on your company server room is not a valid solution anymore. We have all been through a very hard year last year, and we've all been cut from our companies. We had to take our equipment back home to work from home, and it was really a nightmare for everyone. So if you can access your data from anywhere, at any time, any device, and it is secure at the same time, this will be great. Third challenge here is communication and collaboration. How you can collaborate and communicate with your teammates or your team leader, with the management, with the marketing department, with everyone in the team in a very reliable way. And we have here a solution, say, easy to use communication channel, which bring all stakeholders into the picture in real time. This is very important. All right, so these are the challenges. And now we are going to look into the engineering solution for it. So just again, a little bit back to when engineering started, engineering 1.0. This is the industrial era. It's in the 1700s where the first steam engine being produced and other innovative products. In this era, they were just using just pen and paper, blueprints, things like this. Then engineering 2.0, where is engineers start to use 2D application, 2D drawing applications. There are not less use of blueprints, and now we are using software to create our designs. So this was a very good step. Second last step was engineering 3.0, where we start using 3D application and simulation and prototyping. This was in between late 900 and early 2000. The current era that we live in is the engineering 4.1, and the characteristic of this era is model-based approach, less time spending, recreating and interpreting data. Each stakeholder have access to information needed in a specific format, 24/7 accessibility through any device, concurrent engineering, sharing data via automated delivery and update mechanism, system integrations. This is all what is required for us to adopt today in order to step from being good to be great. So this is our solution here from the Dassault system. It is a new platform called 3D Experience. And in this platform, we bring together more than 13 brands that involve in design, simulation or design verification, data management, manufacturing, project management in one single platform. This platform is currently helping 11 industries, including automotive and industrial equipment, even life science. The main reason behind using this technology is to, transfer from this model to this model, where you can save time and money. So you get your design earlier, get your market earlier, and benefit from saving this time and benefit from the money that you are going to gain as a result. These are all just focusing on the mining industry, and they suit themselves to the mining industry. Although as well, they apply to many other industries. Right, so who provide this solution here in Australia and New Zealand? So Center Innovation is the company that I'm working with, and we have been here in the industry for about 27 years. We provide software, hardware, system, and people. So software, as you can see here, a list of software including SolidWorks, 3D Experience. Hardware, we provide our own hardware workstations. They are the fastest in the planet. And systems, if there is no software that can fit in, or you need a software, we provide this software for you. Sharp Task and Data Suite are examples of the software that we provide. We also have a recruitment arm here, where we can provide high talented contractors and designers and engineers. All right, so let us look on our customer base here that are related to mining and offshore. Many of the customers are shared with MacForge as well, like Index, Russell Minerals, and so on. The other names are all famous for this industry, as you can see. They are all adopting or in a way to adopt this technology. All right, so let us have a look on a live case study. And our case study today is a mining equipment called Bolter, Redmond Bolter 77D. So let us have a look on this equipment. So this equipment actually secure the mine ceilings by steel reinforcements, as we will see now. So get into the mine and start securing the mine ceiling with steel mesh reinforcements. So this equipment here has been designed, and when we say design, this is not only just 3D modeling, this is everything from 3D modeling, assembly, electrical design, electronic design, cabling, design verification, even manuals have been created by SolidWorks and the other products that we provide. So this is a product life cycle here. As you can see, stakeholders here included 2D to 3D design, project management, simulation, assembly drawings and bill of materials, assembly instructions, data management, and working with large designs as well. Okay, so it is demo time. Let us have time now to look into our platform. Just gonna bring my platform here. So this is the 3D experience platform that we were talking about. It is looks like Facebook, if you would like. So it's very easy to use. I want to share, for instant, a post here. You just go and start sharing my post. Actually, the real case studies that we are going to work on. So we have a problem here with the boom knuckle, and we want to discuss this with my team member that are members in this community. We're just gonna post here a post saying, all right, boom. I can't type right. All right. From here, my team members will start interacting. My team leader will start creating what we called here a change action. So he will provide an instructions for me or for the engineers that will be responsible for handling this operation to start working on the knuckle and the knuckle assembly. I just believe the performance is a little bit slow over the Zoom meeting. Yep, we have our action here. So all this is controlled and stored on the cloud. So I can see here my change actions, the member who is assigned to this action, the progress changes, and so on. I also have a task here that has been assigned to me. And in this task, I can open it, and I can see here the requirement: design change required, part failing during operation, need to perform simulation analysis, and 3D print optimized model. So you can't get it wrong here. Also, I have all the parts and the assemblies that are involved in the process attached to my task. So I can just simply move the task from to do to in work now. Using the same platform, I can access SolidWorks. And for you who do not know what is SolidWorks, it's a design and simulation and manufacturing software. And from here, I can have a full understanding on the models that I'm working with. Can also test its motion. Have a look here and zoom in into the part that is on question. And I can start an analysis simulation study on this model. As you can see as well, I have a full control on the documentation here. So I moved my assembly to in work. I can also change its maturity to prevent anyone from changing it to freeze the design, so no one can have access to this design and start producing it. I can create something like a simulation case study, as you can see here, defining all the materials, constraints, connections, adding bolts, bearings, and all of this stuff. All of these are out of the box functions that you can bring into your simulation study straight away. Can add my fixtures as well, my loads, and I can get my results. So I can see my stress results here, different stress results, displacements. Can dig into the model itself to see how it's behaving. Can look into localized stresses. And I can also see the safety factor or factor of safety on the model. Okay, from here I can dig in more and just focus on the knuckle assembly. And I have created here several scenarios for optimizing and just running what-if scenarios. So I have many, I have 3 studies here, and again, can have a look on the stress results, displacement results, stresses in section view here, just localize stresses here, stresses on the bushings, stresses on the knuckle, and even the contact pressure. So all this will give you a very good understanding on what are the factors that affecting the design of this part. From here, I can focus on my final assembly here, or secondary assembly, and I can run another study, again focusing on just the components that I want to assess. After running this study, I can run a final, what we call here a design study, or what-if scenario. So in this what-if scenario, I say, all right, I have some parameters here that I'm going to vary, like this radius here and the wall thickness here. I want to vary them from 10 millimeter as a minimum, maximum 40 millimeters, and for the width from 10 millimeters to 30 millimeters. Have a stress constraint here. I don't want my stresses to be more than 250 megapascals. And I want to minimize the mass as well. And as a result of running this study, you can get here to the optimized design. So if we go here, we start from the initial design where the radius was 30 millimeters. We reduced it by to 12 millimeters, 12 millimeters, width from 30 millimeters to 8 millimeters. This is resulting in a mass reduction from 18 kilograms to 17 kilograms. On the spot, straight away, applying the optimal design will update my model, and I can open my model now, get this model ready for 3D printing. So just one step a way to go here to my 3D printing application. And from here, I can select my MacForge X7 printer, set my part in it, and then find the best orientation. So this is scale 1:1 of the MacForge X7 platform with comparison to my parts that I'm going to print. Right? Can have some information here about if my part will print all right. Do I have any problems with the wall thickness? If I have any problems with the gaps, where the support material will be added, can also select the material. Anthony will tell you more about this process. My final step here will be to save this file as an STL. So I just gonna go and save my file here as an STL. I'm just gonna save it on desktop for now. My desktop, my STL file is ready to go. Just one final step before I do this, I was just gonna create something called an interactive PDF, just to send with the STL file. So I can get all that the person who is gonna prepare this model can cross-check the 3D printed model with the required dimensions. So this will be the format of the PDF that I'm going to send with my STL file here as an attachment to the PDF. This PDF here is an interactive PDF. This means that I can change views, zoom in or zoom out, rotate. And so on. After I'm done with all this, I need to go back to my SolidWorks application here and tell everyone that I'm done and close my, so I can go here, save my design. While this is saving, can go to my platform and change my task from in work to complete. And even maybe just add the deliverables first. I'm going to add my STL file. So it's just a matter of drag and drop. And then I can just move it back to complete. Everyone now understands that I finished my design and it is ready to go. My last step, part here in my presentation, just gonna want to show you here some case studies. And the first case study here that I'm going to share with you actually is the same case study that Anthony shared. So Russell Mineral here from Australia, using our application here, they managed to shorten the design time from 3 months to 7 days. What an improvement. 3 months to a week. This is a very good improvement. Reduction of code preparation time from a week to 1 day. Something like code drawing generation from 6 hours to 15 minutes. The other case study here is Getman, and we are sharing this case study because these guys actually started very early. So they started in the 1954. So they started nearly in the era where they're still using blueprints and pen and paper. And they managed to adopt this technology. And in the picture here, it is just 2 screen captures of this is a CAD model, and this is the actual model created by after manufacturing it. If I return back to my 3D experience, I can actually have here what we called media link, and I can jump straight away to the Russell Mineral success story from the source system. And you can read the code that the guys wrote themselves. What we need to understand here, that in order to get yourself from being a good company to being a great company, you need to manage and get into the strain of the engineering era. So if you're still in using engineering 2.2 or even engineering 3.0, it's time to switch to engineering 4.0. All right. So at the end, we want just to let you know that the future is in using one ecosystem, end-to-end solution. There is no room now for just using a very powerful CAD software without having maybe 3D printing application, for instance, or without having a platform to manage your data, to interact with your team. I believe this is the end of my presentation. I will pass the presentation back to Anthony. Thank you, everyone.
Thank you so much, Amgad. All right. All right, so it's very interesting to see the workflow, the software workflow that Amgad presented. What happens now is that, I guess Amgad, may be based in Perth, but the mine is in Kalgoorlie. So he may actually send that to the design engineer on site, and they'll prepare the file for 3D printing, or the engineers in Perth could prepare this themselves. But what happens after that is that it is uploaded into Eiger, which is Markforged's cloud software. So this is the part that you see here. So basically, you can bring it in. You can understand the mass, the cost. You can set the settings, all that sort of stuff. But the really nice bit is the ability to see inside the part and how the composite system actually works. So for this case, what I've done is I've routed carbon fiber all through that part on the outer surface as a very sort of simple, I guess, solution, very quick one. What you can do, depending on the forces involved, is that you can put carbon fiber specifically in areas that need extra reinforcing. So once you've checked that out and you're happy with how the carbon fiber is routed and the strength properties of that particular part, you can then double check that you're happy with the settings, and then simply print to the cloud. So for this particular application, basically the purpose is to validate the design without spending big bucks on CNC. So if you can print this part, which is a very strong part, and you can validate that design, that makes it easier to produce the end use part. For this particular part, with our composite system, it's similar to the strength of aluminium. So for the part that Amgad was showing, I would say steel would be the best end use application for that particular one. But for this case, this is very good for functional validation. Okay, so moving on to the last slide. So an introduction to Markforged. So I haven't actually said who we are as a company. Basically, Markforged are an OEM of what we call the digital forge. And the digital forge is hardware, software, and materials. And as Amgad said, if you have an ecosystem, you're able to control the end result. So basically what we believe is we're selling the end use parts here. What matters is the tolerance and the strength of the end use parts. And with that digital forge, you're able to ensure that you're able to get strong parts with a good tolerance. So with that, I will move on to questions Q&A. I believe that there have been quite a few questions answered already by Alan, who is based in Singapore. And I'll just have a quick look to see if there are any other questions here that we can answer. Okay, so there's a question here from Marco. What materials can you use and mix? Do you have access to an existing library of parts? And do you have, do you have to always have a design? So basically, we have the composite system and the metal system. The composite system combines continuous fiber with a base matrix. The base is a mixture of nylon and chopped carbon fiber, whereas the continuous fiber can be Kevlar, high strength, high temperature fiberglass, or carbon fiber. With our metal system, we have a few different materials, including Inconel, copper, a variety of tool steels and stainless steel. In terms of your question, do you have access to an existing library of parts, or do you always have to design? Typically, when people are looking for an additive manufacturing solution, they want custom parts. So the way that they produce those parts is by having in-house design engineers or getting that outsourced. There are plenty of parts online, but if you're serious about the solution that you're trying to implement, then it is best to have a designer design those parts for you. Okay. All right. There was questions about accessing the presentation afterwards. This presentation will be accessible, and you'll be emailed, with a link to that presentation. Okay, so there's a question here. Do you have a good surface roughness or require additional machining to achieve the final surface requirement? So I assume you're talking about metal parts here. We do have some basic roughness data, but typically with our metal 3D printing, it's analogous to sand casting. So what we find is that a lot of customers who are printing in metal, if they do need that super tight tolerance, they identify the surfaces that need that tolerance and are able to machine those surfaces. So they're able to get the complexity of the part, but when you do need those surfaces within that tolerance, you can address that through some machining. But a lot of parts, a lot of end-use parts for metal, we do find are okay straight off the printer, but some do require machining. Okay. In terms of strength of our parts, we have a question from the same person, from Tan. If you can reach out to one of our partners in APAC or Singapore or wherever you might be based, we can certainly share some of those data sheets on the strength. We do have a few data sheets online on our Markforged website that talk about the stress strain characteristics of all of our materials. Okay. Do you have videos of your 3D printers in action on your corporate website? I believe there are lots and lots of videos on YouTube with the 3D printers in action and a few snippets on our website. So if you explore our website, there are a few cool images there. And we have a couple of questions here around accessing the SolidWorks assembly file. I believe Amgad is typing that answer as we talk. Okay, final chance to ask a few questions. Right, so we have a question from Saxon Druce. Do you have data on the thermal conductivity of the carbon fiber material once printed into the part? We do. We have done some testing on thermal conductivity of our base material, which is onyx. However, in general, onyx is an insulator of both electricity and heat. But typically, when you're designing these parts, all of these parts are custom made. So you design where the routing goes into these parts. So therefore, depending on the settings of the printer, the thermal conductivity is going to be different. What is much more common is customers' concerns around electrical conductivity. And we do have a material that is specifically designed for controlling the static discharge of material called Onyx ESD. So we do have a lot of data based on that particular material and the electrical conductivity of that material. The key with that material is that it's surface resistant. So it doesn't matter what's happening inside the part with their carbon. What matters is the surface resistance, the electrical resistance. So we have a question from Marlone. So does the printed part have shrinkage similarly to grey cast iron in a casting process? So I guess with our metal technology, it is based on MIM. So basically, we have software that controls the shrinkage. So if you reach out to one of our applications engineers or partners, they'll be able to take you through the detailed process. Basically, the part you design is the part that you get out. There is some shrinkage in the sintering process. However, this is taken account for in the software, so that you end up with the same geometry as you designed. Is the supply of materials only available through Markforged? From Alex. So yes, we do have a closed ecosystem. So the reason why we have that is that so we can guarantee part strength and part performance, as well as tolerance. A lot of 3D printing companies and CNC and various manufacturing companies take a different approach. However, what we find is that the best way to produce a good part is to be able to understand the materials extremely well, to have control over the materials, so that we can integrate our software, our machines, and our materials to produce very good parts. We have a question. What is the scalability of additive manufacturing technology? Is it mainly for smaller / specific parts? And if so, can we expect to see something more large scale in the future? So in terms of the scalability of additive manufacturing, we do find a lot of companies start off by producing end-use parts. The thing with additive manufacturing, if you compare it with something like injection molding, which is extremely scalable, is that if you're printing one part, it takes X amount of time. If you're producing 100 parts, it takes 100 times that. Whereas with injection molding, to produce one part is extremely expensive, but to produce thousands of parts is super cheap. So that's the difference with 3D printing. The way to achieve scalability is that typically customers start off by printing end-use parts. As they grow, they either grow into a print farm, or they start producing the jigs and fixtures and the tooling to produce their end-use parts. So it all depends on production volumes, and there'll be a technology for each level of production volume. Okay. I'm just having a look at here. Is the supply of materials only available through Markforged? Yep, so that's to do with our closed ecosystem, and that is available through our partners or through Markforged. Okay, are there any case studies that show the return on investment for a metal printer in this application? So we do have a lot of case studies that show return on investment. Typically, we compare the cost of producing the part traditionally to the cost of producing the part with the Markforged system. On our website, we do have a lot of those costs compared, and we do have a lot of articles that show what the return on investment was. Obviously the return on investment is going to be a little bit more personal to each company. So if you can reach out to one of our partners or application engineers, we can have a detailed discussion on what that return on investment would be and compare it to other companies around the world that have had their return on investment. But the return on investment could be anything from, between, you could achieve it almost immediately depending on the cost of the part. It could be 6 months, it could be a year. It all depends on the parts that you're looking to print. So some great questions there. All right, so we're 6 minutes past the hour. If there are no more questions, I will leave it there. Actually, we have one more question around the speed of metal 3D printing. This is a question that I guess is best discussed if you reach out to one of our application engineers or partners. And the reason why is that the process involves batch manufacturing. So depending on how you configure the batch of parts, the speed can be optimized. If you're looking for like a speed of producing one part, what is the fastest period of time you can produce a part? You can produce a part in 2 days. But if you want to produce multiple parts, then it's good to have an analysis into how many parts you want to print and how many parts you want to fit into the sinter. Okay, that seems to be all of the questions. Thank you so much for joining, and thank you, Amgad, for your presentation. I find this industry fascinating, and it's great to follow it and its evolution into Industry 4.0 and how it's reacting to the challenges that we're seeing in these last couple of years. All right, thanks everyone. Have a good afternoon.